Okay, yeah. Okay, so yeah, again, thank you everyone for coming to our tutorial. Next, I will be talking about the text-to-image generation and how do we actually produce visual data. So still starting from these previous figures, previously the previous speakers have talked about the bottom left center about how can we consume visual data to train vision understanding models that can have good image representation as well as building more universal image understanding model. Next, we will try to touch a little bit on the inverse direction on seeing how can we go the inverse direction and produce visual data. Specifically, in this tutorial session, we'll be focusing on the so-called alignment perspective in producing the visual data, that how can we get data that actually align with the human intent so that we can make such data actually useful. So starting from the basics of text-to-image generation tries to generate high fidelity image condition on the text input. So this is a special problem under the conditional image generation that tries to not only generate high quality image, but also wish it to be semantically related to the input condition, where in this specific case to be the text description of the image that we try to have. So instead of trying to give a comprehensive overview of all aspects in the text-to-image generation, which as we overviewed in the bottom figure is evolving very fast. So in today's section, we try to introduce the text-to-image from the so-called alignment perspective about how can we have models that better aligns with the human intent, or in another word, how can we have the systems more easily help users generate the exact visual contents that they are imagined, or just to have the text to image easier to use. So zooming into this broader motivation of having the more aligned text to image generation model, specifically we'll be introducing related works mainly from the following 4 aspects. Starting from the controllable generation, that in addition to the image description, that is the text part used in most text-to-image generation, in some scenarios, we might be interested in having additional input conditions or input channels that the users can use in order to make the generation easier or helping them more easily convey what they actually intend to draw. And next is the editing part. So editing is also a very important channel in the alignment, that in some scenarios, we might be mostly happy about the image we generated or already have, except we might want to tweak a little bit. For example, it can be either the image style, we wanted to change the style a little bit, or spatially, only at a specific location, we want to add or edit an object. So in this way, editing provides us a tool to keep the majority of the image, but only to modify it a little bit to perfectly align with what we actually want to generate. Next, we'll talk about better following text prompts. So although text-to-image models are trained with the hope that it can generate an image that is semantically related to the input text prompt, as we will show later, unfortunately, this is not always the case, that sometimes, especially when the text description becomes more complicated, the model might just decide to overlook a certain objects or get confused with some detailed attribute description. For example, apply the color onto the wrong objects. So there has been also a line of research exploring how to have the model more strictly following the input text prompts, and in this way, provide a way for people to more easily generate the exact image they are thinking about. And finally, is the concept customization, that sometimes we may wish to have the model to have some visual content we already have, for example, our own pet dog or a specific cartoon characters that is just designed by ourselves previously, and apply these visual entities onto different scenarios. So those visual entities might be difficult to specify by the natural language. For example, how exactly our pet dog should look like and differentiates them with all the remaining dogs. And instead, it might make more sense to have the model take such additional concept and somehow customize an open-ended general T2I model into our specific use cases. So these are some interesting alignment-related generation topics that we wish to cover today. Before diving into all of those exciting works in all those sub-directions, maybe let's first have a quick overview of some basics in the text-to-image generation. Again, text-to-image generation is a conditional generation problem that takes text as the input condition and tries to produce an image that is both of good visual quality and meanwhile semantically corresponding to the input text prompts. This is usually done by using the paired image text data, where the text part in this image text pair is used as the input to the system, and the corresponding text in the pair is used as the training objective. So by training the model to actually mimic or reproduce this image, it not only enforces the model learn to generate reasonable images, but also because the image text is paired in the training samples, it implicitly learns to generate image that is semantically corresponded to the text input. So zooming into the image generation part, here are several representative image generation techniques. Starting from the classic generative adversarial network, or GAN. So GAN consists of a paired generator and a discriminator. So generator tries to generate an image from noise conditioned on the text input, which competes against the discriminator that tries to distinguish whether the input image is real or fake. And by having these two counterparts compete with each other, generator learns to produce more realistic image, where now the realistic is actually defined by whether this discriminator can actually distinguish whether it's fake or real or fake. Next, onto the more recent approach, one representative is the autoregressive transformer-based approach. So such method will usually take a paired image tokenizer and a detokenizer with the core idea of converting the image first into multiple patches and mapping each patch into a discrete index, where this index indicating the refers to the index of a specific token in the codebook of the image tokenizer. And then with this paired tokenizer and detokenizer, for example, a VQ GAN, we can project an image prediction into a set of discrete tokens still arranged as a 2D matrix. Sorry. And after discretize the image prediction, we can then have the model predict tokens one by one following a specific order. For example, usually starting from the first row from left to left, then the second row, so on and so forth, and we can complete the entire image. And then with this predicted set of discrete tokens, it can be sent back to the detokenizer part to recover the final image we try to generate. And instead of predicting those discrete tokens one by one in an autoregressive way, there are also some very interesting work showing that we can have certain scheduling policy that at each step, we generate multiple tokens jointly, so that instead of having to reproduce a quite long steps, we can greatly speed up the inference process by generating multiple tokens at the single step. And finally is the diffusion. So diffusion involves random noise into the image as a multi-step denoising process. So the goal in each step is to predict a meaningful, semantically meaningful noise to subtract from the initially randomly initialized noise, so that finally we can end up with an image that is both of good visual quality and semantically related to the text input. So next, we will use one specific model, the stable diffusion, as a closer look example to help us better understand some like what a text-to-image model might look like. So here we choose stable diffusion for several reasons. The first is that this is one of the very popular open source model, and as we'll show later, many of the alignments work we are going to introduce later today are actually built based on this model. And also, it represents one of the diffusion-based generation method. And finally, how the text actually operate on the image, which is one core problem in text-to-image generation. The cross-attention mechanism are actually also shared by many other non-diffusion-based methods, for example, in the autoregressive generation. So we think this might be a good example to help us better understand how a typical text-to-image generation model looks like. So let's start with the Stable Diffusion's architecture overview, or short for SD. So as shown in the right side, the architecture mainly consists of 3 parts. So in the leftmost is a pair of variational autoencoder, or VAEs, encoder and decoder, which as shown in the top right can take an image and project it into a latent, which the diffusion process actually later operate on, and also take this latent and use the paired decoder to recover the final image, or the original reconstructed image. And the second part is on the rightmost side, that is the conditional encoder. So if specifically when we are talking about text to image generation, that we take text as input, this conditional encoder can be a clip text encoder that takes a language sentence as input and produce a set of word embeddings. For example, a typical magic number is 77, which is the maximum length of the clip text encoder. So each word will have a text feature encoding, feature, which are then sent into the center part, which is a core part of the model, the conditional text condition denoting unit. So the process might be more clear if we have a closer look at the right side inference flow, that assuming we have the model already being trained, how can we, so in the inference time, what does the latent flow look like so that we can end up with a good looking image? So starting from the top side of the right side image is the input to the system, which basically consists of visual and text part. So the text is on the right side, which is a sentence input, which is then fed through the frozen text clip text encoder and producing a set of text features. For example, a typical dimension is 77, which is the maximum number of word tokens, times a text embedding length, for example, 768. And then in the center is the visual related information, or the latent, because the Stable Diffusion actually operate on the latent space. So this latent contains the visually related information. Basically, this is where we store the image information that we try to generate. So as mentioned later, this latent actually starts with a random noise, and then this visual and text information are sent into the center, the largest block, which is the text condition, the latent unit. And the goal of this model is that we try to train it to predict a meaningful noise to subtract from the previous latent, such that the output of this unit in each round will be sort of a less noisy version of the latent. And this process is done repetitively for multiple times, as visualized in the bottom, the gradually denoising process, so that in the final round, hopefully we can end up with a good latent that we later send through the decoder of the VAE, that hopefully can give us a good looking image that is also semantically related to the text input. And as we might see, actually the core magic, or the core part, is mostly in this center text condition unit, that how does the framework actually look like, so that it can predict meaningful noise to subtract, which finally ends up with a meaningful image that we want to produce. So here we also further zoom into this text condition unit on seeing how the text condition actually operates on the image feature, or the latent, so that we can produce a reasonable image. So at a high level, this is a unit. So at the bottom left side, we just show some very abstracted view of basically what the unit look like, which consists of a series of downsampling block as well as later upsampling block with some skip connections in between. And zooming into any of these specific blocks. So here we show a downsampling block, which is also the same for an upsampling block. So each of these blocks take both the latent, basically the visual information, the text information, as well as the T. T indicates the denoising timestamp, telling the model basically how noisy the input latents might be as input, and feed through this block and try to produce the next steps of latent. So inside this block, there are mainly 2 operations. One is the image text cross attention. The other is the convolutional downsampling or upsampling layer. And further zooming into this image text cross attention, this is basically actually where the text and the visual features see each other. So if we're looking into that, this is basically a quite standard cross attention, where the query is the visual related information, basically this latent, except we add some like time step related information. And the key and value would be the text word embedding. So again, the 77 refers to the maximum length of the text sequence. And basically we'll do the attention mechanism. And as we can see, by simply computing the attention maps by producing the query and key, we will end up with an image text attention map that shares the size of the spatial dimension, height times width, times the number of text tokens. Or in another word, during this cross attention process, each word in the input text prompt will attend to spatially to the latent, so that each word will attend to different parts of the latent. So this is basically one core part that how this generation process or how text actually will later influence the generation process. So actually we highlight this attention map because as we will see later, many of the alignment work are actually trying to manipulate these attention maps. So I thought it might be helpful to talk into a little bit more details on this cross attention mechanism. And again, in addition to the diffusion-based or stable diffusion, this cross attention is also shared by many non-diffusion-based methods on how to generate image condition on the text. So I have just talked about some very brief overview of the basics in text-to-image generation. And next, we could continue on to the following four aspects that we talk about in the so-called aligning human intention in text-to-image generation. Again, controllable generation, editing, better following prompts, and the concept customization. We start with the controllable generation. So the overall motivation is that, so the text in a typical text-to-image generation refers to the global description of the entire image. And in some case, it might be helpful to combine such global text description with some other format of optional additional input conditions. For example, either the layout leading to the grounded text description or some other dense controls, for example, mask, edge maps, scribbles, and so on, so that the users can more easily specify the, for example, layout and other aspects of the image if they desire. And by the way, for the later other aspects, I will also just list the related papers on the right side, which due to the limit of time, we might only be able to sample a select of them to give a rough idea about how each of these sub-bullet points are talking about. So next, we will continue with the first part, that combining text with the layout. Again, we start with the motivation. So the text in text-to-image generation, as shown in the bottom left, usually refers to the global image description. For example, for the leftmost image, it can be a description like a dog sitting next to a water bowl. So in one of these recent work, ReCo, the authors try to explore if they can expand the sort of definition of text from the text only, basically containing only text word, into a mix of the so-called grounded global and region description, with the major motivation of seeing if we can have text only describing a specific part of the image. For example, we can specify in the bottom left corner of the image, we want to draw a silver bowl with water in it without having the text description influence any part of the other part of the image. So method-wise, such expansion is mostly done on expanding the input sequence vocabulary. So basically including additional box tokens in addition to the text tokens. And as we might see in some of the previous image understanding work, we have also discussed how to expand the box vocabulary, except now it is used as the input side and also show that they can also providing a more easy way to provide the grounded description where the added box tokens serve as a spatial modifier that only operates on the text to follow it. For example, we can specify in a certain region what this player's appearance and other detailed features that we try to have the model to generate. And the model actually also built based on stable diffusion is then fine-tuned to understand the meaning of such box tokens, so that on the input side, user can generate the mix of such box and text tokens to provide the grounded referring. And other than do such expansion or the grounded control on the input side, another effective way is to expand it with the grounding tokens. So let's first talk about what might these grounding tokens, what information might it contain. So it is actually a mix of two parts of information. One is the grounded text entity, for example, the text word like the wedding cake, and it also combines the feature with the spatial coordinates, for example, the bounding box coordinates, so that the final grounding tokens contains the information of both some part of the grounded text referring, as well as the location of which part of the image this text referring should operate on. And then the study, the GLIGEN study introduced the new gated self-attention layer, which is inserted into every transformer block inside a pre-trained text-to-image models. So this added gated self-attention layers is added to help model understand the meaning of these grounding tokens, or in another way, using such grounding tokens to provide the spatial controllability. So one code design is shown here, basically the gamma hyperparameter, which is zero initialized. So this is quite important as it as during the fine-tuning stage, it enforces that this additional added gated attention at the very beginning does not influence or worsen the original pre-trained text-to-image generation, and it only comes to place gradually during the model fine-tuning so that it can keep the original text-to-image generation capability, but also provide our desired additional channel of the grounding or the layout controls. And as shown by the authors, such method can effectively enable a wide range of such grounded controls. For example, combining text description with the bounding box grounding, key point grounding, and other types of spatially aligned dense conditions. And in addition to box or layout, people are also interested in seeing if we can further include other types of sort of dense control. So here by saying dense control, we mean that the conditions that is usually represented as a 2D matrix more similar to the image. Examples could be the segmentation maps, the depth maps, normal maps, and so on. So one representative works along this line is the control net with the architecture shown on the right side. So the core idea is to copy the encoder part of the pre-trained stable diffusion as an additional conditional branch, which also takes the additional condition as input. And only this additional added conditional branch is fine-tuned so that it can understand this additional condition input. And also, it's quite important that the output of this added branch is then sent back to the decoder branch of the main framework after this specially designed zero convolution, with a similar motivation that in the very beginning, the fine-tuning does not look at any information on this additional condition branch. Instead, it's just sort of a basic text-to-image as in the stable diffusion pre-training. And later, when the model learns to set these zero initialized parameters to be non-zero, this additional branch of condition gradually coming in and achieve our goal of the combination of text and other dense conditions. And also along this line, further extended from ControlNet, recently there are also some very interesting work on building a more unified solution for ControlNet. For example, they try to see if we can build a single model, or more precisely a single additional branch that can operate different type of conditions. And on the one side, such unified model allows a single model that can now take different types of conditions. And also it's interesting that they can now take the composition of multiple different types of conditions. For example, we can now take both the human key post map as well as the segmentation map as two conditions in addition to text and generate the corresponding image. So all previously introduced method that would actually require certain extent of model fine-tuning, either the entire framework or specific adapter-like layers. And other than the fine-tuning, there has also been some very interesting recent work on seeing if we can have such additional guidance, but only in the inference time. So, so the universal guidance for diffusion model is one representative work, where the core idea is to extend the idea in classifier guidance to expand the classifier in the classifier guidance into the general guidance general discriminant guidance. So here, let's take detection as an example, where specifically for the detection case, this letter F indicates a detector, for example, fast-SNN, which operates on the intermediately generated noisy image Z0. and it will compute the loss with a ground truth label C. So this here, by saying ground truth label, basically it means the exact layout that we try to guide the model to generate. And finally, it will compute some object detection loss indicated by letter L, where this numeric value is used to guide the intermediate generation process so that the generated image would better follow the input boxes, for example, shown in the right side image. Although, as we may see, it didn't follow that strictly compared with some of the previous fine-tuned method. It's still quite interesting that we can being able to achieve such inference time guidance without explicitly requiring the model to do fine-tuning. So previously we talked about controllable generation, and next we'll talk about the editing or image editing. So editing is also another important channel in the alignment in T2I generation, with, again, the motivation being, in many scenarios, we might have an image that are reasonably good, but we want to change a specific part to make it a perfect line with what we intend to generate. So editing contains very different aspects. For example, the image content we try to edit, for example, spatially for a specific region or the global image style, as well as how we specify the editing instruction. For example, describing the final image we want to have, describe the object's region we try to edit, or just the instruction like style, for example, make the image look a different style. So next, we will sample several representative work, try to give a brief overview of some representative works in editing. Yeah, please. Starting from the first is the spatial blend, which is the latents. So assuming we have already know the region to edit, we can apply a spatial map that only operates on this specific region. And we can just blend the latents where the foreground is generated by our input text and the background, it just keeps the original image, so that by spatially blending them with the given mask, we are able to generate the new edit image, just simply editing the content inside this mask region. However, having a mask is sort of a strong assumption, as it might be difficult for users to generate, and the model generated masks are not always that reliable. And also the edge in this hard blind of the foreground and background might have some generation artifacts. So some other study also show that specifically for the generated image that we try to edit, one effective way might be just to directly manipulate the image text cross attention map. As we mentioned later, this cross attention map would implicitly have some spatial attended patterns so that it can achieve certain editing operation, for example, word swap, adding new phrases, and attention reweighting. Or more specifically, it will maintain two sets of cross attention maps. So one is for the original image, so basically show for this square-shaped lemon cake that is the image we previously generated. We might want to keep the overall visual looking of this image, but try to just make it more monstery, than basically a monster cake. So if we just use this new prompt of monster cake to generate the image with the cross attention map empty star, it will be a reasonable image, but it will basically visually looks very different from the original image that we try to edit. So this study showed that we can simply have a clever way to combine this empty and empty star into the new set of attention maps indicated by this empty head, and just do the generation with this new empty head, so that we can end up with this image show indicated by the goal on the right side, that it both keep the overall visual looking of the original image, but also adding the new contents we try to edit, basically some monster related visual properties. And again, here are just some more visualization of the supported word swap, adding new phrase, and attention reweighting operations. However, being able to only edit the model generated image might be sometimes more restrictive. So there are also studies try to see if we can have editing on the natural image for any photos, for example, our own pet dog, whether we can make it sit, jumping, or doing some other actions. So the core idea of this paper is starting from the original image. So basically the image we have, like the bird standing, whether we can find a corresponding text embedding that are likely being able to reproduce or regenerate this image if we send it through a generation model. So after optimizing that, we'll have the original text, and the text we try to edit, basically the description, like we want to have a photo of the bird spreading head, but spreading wings, but still the same bird. So after finding this optimized embedding, or basically the semantic related to the original image's text embedding, we can simply interpret them or combining them to produce the final image with the same bird, but wings spread. So although like having method to obtain such original text shows a way to achieve some level of natural image understanding, obtaining such original text is not always easy, and as shown in the previous study, it only works well when we fine-tune the model for several steps, which might be a little bit complicated. So intuitively, it might make more sense if the model can understand the so-called instruction text. For example, instead of saying the description that we want to have a bird spreading wings, we can just say we want to have the image, but with the birds have wings spreaded. So basically, the problem is that if we can have pairs of image data, as shown in the right side, as well as the corresponding instruct text, we can simply train an image text condition, an image-to-image model that can do such editing or such appearance changes. However, the problem is that previously there does not exist the data. So in this paper, the authors show that they can use starting from one sentence and use the large language model to generate, one is the edited caption. So basically starting from bird standing into bird spreading wings, as well as its corresponding instruction, basically having wings spread. And then sending all these two sentences, one is using the stable diffusion to convert bird standing into an image. And also we previously mentioned there are some methods that we can edit the generated image, for example, prompt to prompt, and we can use the generated image as well as the paired edited caption to get a pair of samples, basically the bird standing and bird spreading wings, as well as the corresponding text instruction, so that we can train a image-to-image model that can understand the instruction style text editing instructions. And finally, in the editing thread of work, instead of developing single models, there has also been a recent trend of building effective editing system based on the external modules. So here are so one effective is to combine it with some strong segmentation model, for example, the SAM and SEAMs we previously discussed, so that by seeing a natural language description, the model will automatically find the region to edit as a mask and change the visual appearance in that region accordingly. And also another trend is using the large language model as the center to training different tools so that it can know what the editing operation it should do. So in the final part of today's scenario, we will zoom into such multimodal training and talk more about such systems. And we'll talk about controllable generation and editing. Next is better following text prompts. Although we train the model with the hope that it can generate image semantically corresponding to the text condition, in many scenarios, unfortunately, this might not be the case. So there has also been work in trying to explore if we can simply have the model better following text prompts. So one thread of work is doing the text time guidance. Again, the problem is that when the query becomes more complicated, it might have the following problem. For example, the attribute leakage. Instead of generating a red car and a white sheep, it might just decide to generate a red car and a red sheep instead of a white one. And also other problems like interchanged attributes and missing objects are also commonly appear problems in not strictly following text prompts. So one way, as shown in this work, is simply to manipulate the value in the image text cross attention based on the linguistic parsing tree structures to enforce the model to evenly looking at all the parsed non-phrases instead of looking at all words equally, but just to parse out all the non-phrases, for example, shown in here, and enforce the model to assign equal weights when doing the cross attention, so that it learns to look at all the non-phrases appeared in the image. With a similar motivation, there is another work showing that instead of doing such redistribution in the latent space, it might also be effective to adding certain related localization directly on the attention map, with the core idea still being trying to enhance the maximum attention for the most neglected subject tokens, which later derived into this loss that the maximum attention map for any words should be close to 1, that for any words, it should at least attend to one spatial location, which hopefully it will later draw these noun phrases there. So, so again, by adding this additional latent and additional loss and use it to guide the latent, the author also show that it can generate the noun phrases or the text prompts more correctly. And other than the test time inference, there is also a line of research tries to do additional stage of fine-tuning that tries to have the model directly out of box, more strictly following the text prompts. So partly inspired by the success of IL human feedback in the large language model, there has also been works in seeing if we can use reinforcement learning to optimize diffusion models to direct to perform better to better following different downstream objectives, where one of them could be the prompt alignment. So specifically, this prompt alignment could be we use a large multimodal model, for example, the representative lava, to take the generated image and generate a description of what is there in this generated image, and compute the text similarity with the input prompt, which yields a score basically indicating the semantic correspondence between the generated image and the input text prompt. And this score is used as a reward to optimize the original text image generation model. And as we can see in the right side figure, where the x-axis is the number of additional policy update steps. So we can see that by training the model for or tuning the model for additional step, the similarity score actually goes up, which is also indicated in the centered visualization on different text prompts. And finally is the concept customization that sometimes we might want to add additional visual concepts into our generated images, for example, our own pet dog. Again, the problem setting is having several images, for example, 3 to 5 images that we try to generate, but with it of different actions, with different styles, and combine it with other different things. So this line of work starts with customizing one single concept based on several images, and with the pioneer work being text inversion, dream boost, and other related works. So the key idea is to add an additional unique identifier V token into the input vocabulary that the model is fine-tuned to understand. This V token basically means our own specific pet dog instead of any general dogs. And the model is then fine-tuned to understand the meaning of V, where specifically in Dream Boost, one problem they mentioned is that if we can jointly fine-tune the entire framework, it will perform better, with the problem being it might forget what the original or general dog might look like. So they propose to generate several samples for the dog and jointly train it with the reconstruction loss to learn our own dog and the prior preservation loss to remember what the original dog looked like, which have been proved to be quite effective. And also further extended, there are studies showing whether we can learn multiple concepts instead of a single visual concept, where this multiple concept can also be either coming from multiple set of images or an image with a mask indicating different visual entities inside of it. And finally, so the previously introduced method would require the test time fine-tuning, meaning that if we want to add our own pet dogs concept into the stable diffusion, we would need to fine-tune the model by ourselves, which might be inconvenient for the users. So there has also been some interesting work in using the idea of retrieval augmented or in-context generation that at the test time take additional image as condition and tries to achieve the similar goal of concept customization. So finally, as a quick summary in today's presentation, we talk about the following 4 aspects of related work in the alignments in text-to-image generation, starting from controllable generation, editing, better following text prompts, and concept customization. I would like to quickly end up with some interesting discussion, or it's more like an observation. So one is the discussion in the text-to-image generation community regarding the open source versus closed source code bases. So as we observed, there has been quite powerful model in both directions, where the open source community usually would have a more faster support for those kind of additional controlling method as well as those new functions. However, we have to admit that for the closed source models, it might work well for certain, especially certain challenging cases, for example, face generation. We're not that sure why, likely due to the specific or better data quality, but we hope that in the future, these two parts could sort of inspire each other and generating even better text-to-image generation models. And the second is about the so-called consuming and producing visual data, which is related to the bigger scope of this today's tutorial. So such closed loop can be done at different levels, for example, data model training objective. But now if we just simply look at the so-called data loop, basically the understanding model, image to text, and the generation model, text to image, has already shown a quite promising loop in generating data to help each other. For example, many of the generation models we introduced today are already using understanding model, for example, image caption, to produce pseudo data to help the training. And for the inverse direction, recently there has also been some great advancement in using synthesized data to help analysis tasks, which is effective in the few shot setting and in the setting where the data is not that easy to acquire. And in the future, I think this is a very exciting topic of how this synthesized data, to what extent could help the general understanding models. And we're excited to see the future works along this direction. With that being said, that's the end of my presentation. Thank you.